How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at 15.7 Le Chatelier's principle. So objectives will be to analyze what would happen to an equilibrium that is subjected to a disturbance, such as changes in temperature, pressure, volume, concentration, and the presence of catalysts. So let's look at some practice problems. Number one, which of the following equilibria blank will shift to the right in response to a decrease in volume? You may have multiple right answers. So a decrease in volume tells me that the pressure is going up. And whenever you have pressure increasing, you're going to shift to the side that has less gas. So you got to look at how many moles of gas are there. And then look at that. So here in choice A, we start with 2 moles of gas, and then we are in equilibrium with on the other side. Well, there's 2 moles of gas here, and then another mole of gas there, 3 moles of gas. So if we increase the pressure, this A would shift to the left. It would prefer the side with fewer gases. So that's not going to be an option. All right, if we take a look at B, it starts with 2 moles of gas. And then on the other side, well, let's see, there's 1 mole of H2 and 1 mole of I2. There's also 2 moles of gas. So this one will not be affected by that because there's equal moles of gas on each side. All right, for choice C, let's see, we have a solid, so we can ignore that. And then we have 3 O2s. So we start with 3 moles of gas, and then on the right side, there are 0. So if we increase the pressure, which side has less gas? On the right, and that's what the problem is asking for. So yeah, C is looking good, but there might be multiple. So let's take a look. For choice D, we have 1 mole of H2 and 1 mole of Cl2. So we start with 2 moles of gas, and on the product side, there's also 2 moles of gas. So no effect there. Choice E, we start with 1 mole of N2 and 3 moles of H2 gases. Both of them are gases, so we start with 4 moles on the left, and on the right side, we only have 2. So if we increased the pressure, yeah, it's going to shift to the right, because on the right, there's fewer moles of gas. There you go. Number 2. The following reaction is exothermic. According to Le Chatelier's, how could you increase the number of moles of product for this reaction? So we want to shift it to the right, and it tells us that it's exothermic. Exothermic is telling us that the heat is leaving the substances, so it ends up as a product, right? So we end up with energy being released. Sorry, I can't write things, apparently. There you go. So how could we shift this to make more products? Well, if we want to shift it to the right, we can add things. When we add, it shifts away from that side, so I can add SO2. If I add SO2 gas, it'll shift it to the right. I can add O2 as well. If I add O2, a reactant, it'll shift it to the right. If we're trying to make more moles of products, well, if we remove stuff, it shifts to replace it. So if we removed SO3, it would shift to the right to make more moles of product. And how could we remove energy? Well, we can cool it. If we cool it, we're removing the energy, which is going to shift it to the right as well. All right, and if I take a look at the moles of gas, well, there's 2 SO2s and 1 O2. I know there's 3 moles of gas on the left side, and there's 2 moles of gas on the right side. So how can I shift it towards the side with less gas? I can increase my pressure. So there's 5 different ways you could do that. Number 3, what would happen to the following equilibrium if pressure was increased at a constant temperature? So well, let's see, we have an N2 gas and we have 1 O2 gas. So we got 2 moles of gas on the left, but we also have 2 moles of gas on the right. So what would happen if we increase the pressure? Nothing. All right, there's equal numbers of moles of gas on either side. So nothing is going to really change to the equilibrium if you increase the pressure for this one. All right, number 4, given the following equilibrium reaction, how could you increase the partial pressure of H2 gas? Give at least 2 ways. All right, well, if we want to increase more, H2, we want to make more H2, we can remove CO. If we remove CO, it's going to shift to replace it, and we're going to get that increase in H2, as well as we're going to make more CO to replace the stuff we removed. but that is kind of beside the point. So how else could we make more H2? Well, carbon solid, as long as it's there, that won't really affect it. We can increase the amount of H2O gas we got if we increase the vapor, or yeah, I guess vapor. If we increase the pressure of the H2O gas, we add it, it shifts away, we'd make more H2. You could say, I would even accept saying if you removed H2. You know, if you took away H2, you'd make more, but I guess I feel like technically it wouldn't really increase the partial pressure. So I'd be a little iffy about accepting that. Then you could also take a look. Well, there's 1 mole of gas on the left, right? Just the H2O gas, and we got 2 moles of gas on the right. So how can I get that to shift to the right in terms of pressure? We can decrease the pressure. We decrease the pressure, it'll shift towards the side that's got more gas, and we'll make more H2. All right, so those are some ways. Number 5, given the following exothermic equilibrium reaction. So again, it's saying it's exothermic, so heat is being released. Heat is a product, so energy ends up on the product side for exothermic. What will happen to the amounts of products and reactants as a result of decreasing the temperature? All right, well, decreasing the temperature is basically removing energy. So if we removed energy, we shift it to replace it. So it would have to shift towards the right to replace that energy we removed. That means SO2, well, that's going to decrease. We're using up SO2. O2, same thing. We're using up O2 to shift it to the right. SO3 is going to increase. We're going to make more of it because we're shifting towards it. And then you could say, you know, the energy gets replaced as well. All right, number 6, explain the effect that adding a catalyst has on equilibrium. All right, so equilibrium, we got this potential energy diagram, and we know that, you know, let's look at an endothermic, for example. Here's my equilibrium. I got a forward process, but I also have a reverse process. What a catalyst does is it lowers that activation energy. So both processes, the forward process is easier, but so is the reverse process. So overall, it has no effect on equilibrium. It may help achieve equilibrium quicker. Like say, for example, you had a setup and you're like, all right, it doesn't instantaneously reach equilibrium. It's going to take some time. If you add a catalyst, it'll quicken that process, but it's not going to change the concentrations or the levels at equilibrium. All right. So yeah, hope you found that helpful. See you in class. Okay, bye.